Norton, equivalent circuits and how we reduce things, but this time I'm going to talk about with dependent sources. And yes, you can take Thevenin Norton circuits and you can decide that, hey, maybe I could actually take the dependent sources and do manipulations, but you must be careful that you don't lose like the voltage you're depending on. So if you can do it fair, well, I'm going to try to avoid not doing that here. I just kind of sort of say what are some other ways I can solve these circuits, and I'm going to look at three of them. The 1, 2, and 3, and sort of take a look at how we'd approach it. Well, this first one is actually fairly straightforward, although initially you'd look at it and go, oh, right, there's some things. It's like, wait, I've got this current source here, and I've got these resistors. What do I do with this? Well, the first thing you notice is I have this voltage, which is going to be the voltage across this one-port network no matter what I do, and that voltage is going to be across these two resistors. So this current source and the resistors are in parallel. So I could think about if I had that voltage source, I know that given that voltage source, this is in parallel with it, V1, basically it looks like a resistive voltage divider. Cool, right? So it means that I can say that V1 is half of V because these two are equal resistors. Well, what that immediately does with the circuit is that makes this, V1 over 5k ohm now look like V over 10k ohm. But wait, it's the voltage across it, and the current is going to be related to the voltage across it. Well, that actually does reduce down to a resistance, and so as a result, I get this circuit, which is now looking fairly, a lot more reasonable. In fact, nothing depends on V1 now, so I can kind of ignore what's going on with that. So I now have two resistors in series. That gives me a 10k and a 100k, and then that gives me the parallel combinations about a 9k resistance when I'm done. So that works out pretty well. And this is the Thevenin Norton equivalent. It just turns out it's an equivalent voltage source of 0. And that's a perfectly allowed approach here. So that would be the first one. Now imagine I take a second circuit. And for the astute among you, you might look at this and go, this feels almost like an op-amp circuit. And it kind of effectively is with, an inverting gain of -1. If you don't know that, that's not a problem here, because still the circuit is what the circuit is. And now I'm going to ask, well, I've got an input, I've got my one port here. I'm going to ask, well, what happens to my input current here? Well, I can start by basically saying, well, what is the input current through the sort of series of these two resistors? Because no current is coming down out of V1. There's nothing for it to go to. So I can look at it both what goes through both resistors, as well as I can say, hey, what's actually happening if I just look at it for one loop, for example? And I know that that current through the resistor is going to be the same either way. So what is the current looking the voltage across both resistors or looking across one resistor? All right, so as a result, now that gives me one equation here. I can do a little bit of math with this, realizing also that, I know what this V1 is and what that voltage source is going to look like because it's already been put in here. Do a little bit of math on this, and I get a couple interesting pieces of this. One of which is that V1 is going to be, V minus 2VA, whatever that VA term is, over 1,000 because I have this really large gain. This is one of those wonderful properties of when you do like op-amp circuits, because you realize that, hey, there's an intermediate voltage here that's moving very, very small. Sometimes people can call it a virtual ground, although one always has to be a little bit careful that you don't get yourself in trouble there. But it is a useful intuition. So it's a very small voltage where maybe, VA might be a volt and V might be a volt. V1 moves like 1 millivolt. So it's a very small voltage, and this is a very useful concept. Well, once you go through this part of the math and you substitute V1 back into this voltage source and work through it, what you find is you get this equivalent circuit, which is, you can start with a 20K here. This is now approximately related to V. Notice I'm using V now instead of V1 because V1 is the term I want to get out of there, so I can solve this. And I get something that's approximately minus V and approximately 2VA at the bottom of this. And you go, that's great. Well, okay, now we could kind of rethink what is the loop equation, what is the loop and voltage equations around this. And I can get current equals to this equation, which then gives me a bunch of 2's over 20K, which is nice. Divide the 2's out, and I get just V minus VA over 10K, which is one way of reducing this down to a 10K resistor and a VA term. And that turns out to be your Thevenin voltage case. And so that works out really well for your 2-port there. We could also do a Norton equivalent of that by just sort of transforming it. But that's actually what you're looking for. For now, for those of you who are thinking about this as an op-amp circuit, you're realizing, that's VA. This is going to be near to ground, so that means this voltage is nearly VA. And you think, oh, well, it's like VA and a 10K ohm resistor. So it's exactly the intuition you would expect if you are familiar with those kind of circuits. If you're not familiar with this kind of circuits, it still turns out to be a very useful way to kind of solve this. So if we take a look at a third one, now this is a more interesting circuit. This is a typical kind of circuit that you might see for a it shows up in lots of different transistor amplifiers. In particular, if you're asking what happens like a cascode current source or other kinds of amplifier structures, you'll see this all over the place, right? And so you start off with a structure, and you can start off by realizing, okay, I could say, well, what is the current coming through here, and talk about how to, sort of write a nodal equation at this node and write nodal equation effectively at the back node, at the bottom node. And I realize that current has to be the same, and I can equate those two values. And you think, cool, I can now write something. One of the easy things here is that voltage V is going to be related to V1, and I could kind of do some very similar concepts there. This gets you quite a ways in because it looks like the equivalent circuit looks something of this form, which gets you almost all the way there, although it could be a little more complicated in some ways for solving it, but it's actually useful to kind of see where it's going. One of the nice things you do see out of this is that one way to talk about what would be the equivalent Norton current source is to say, okay, what would happen? What's the current that flows through here if I assume this voltage is shorted out? And I'm going to look at what is the current that's going through there. Well, if this voltage goes to 0, effectively I have this control current source goes to 0, because now I know that's in V, not in V1. The voltage across these two resistors is nearly 0. There could be a little bit of voltage in here, but very small in terms of what you expect. You get two of them with 0 across it. You're expecting that's going to basically pull nothing out of it. So the current really is just the 0.15 milliamps coming through here. And so that's kind of what you get for your current sources is, 0.15, 0.1 milliamp. Okay, it's really 0.15 milliamp. That's coming through there. Okay, that works out really nicely in terms of your Norton source. So it'd be 0.15 milliamp for the Norton source that you would get there. Great. So then the next question you ask is on the equivalent resistance. Well, how do I look at that? Well, one way to do this is always then turn off all of the independent sources. And so that might be a nice way to think about what happens for this circuit. And you could build it from here and find it, and that's a really good way to solve for the circuit as well, and nice way to kind of look for the resistance there. I'm going to take a different approach just to show a different approach on this. Is to say, imagine that I have this, and now I'm going to turn this current source off. So now I have this particular circuit. Now it's only going to be a dependent source and resistors, and you think, okay, I could solve this, but one of the and I could write some nodal equations and so forth. One of the nice things about this circuit, though, is if I look at this equivalent resistance, right? So it's basically going to be I'm going to say apply a voltage and look at the current that's going through here, right? So it's going to be whatever that voltage I would apply divided by the current that's running through this node. Well, one way to think about that is to say, well, I have like an intermediate voltage V1 here that's across this resistance, this 1K resistance. And one way to think about it is to say, well, what is that? I could say, well, what is the change? I could say, what happens with V1 in the game? And one way to think about it would be, well, I'd really love to have if it was V1 over I, because I know what that is, because that's right here. That's this 1K ohm resistor. That'd be great. Well, one way to think about this in this linear system is then to say, well, that might be the same thing as saying V over I, multiply both the numerator and denominator by V1 and see what you get. And then separate out, well, I get, obviously that's 1, I can do that. Well, V1 over I gives me the 1 kilo ohm, and then I'm just looking for V over V1. So I'm looking for a gain term. And there's some intuition to this that's quite useful, actually, in looking at the circuit, in terms of certain gain I might get out of this. I can certainly write the nodal equation out of that, looking at KCL at this node, and sort of seeing what am I going to get by both the V and the V1 term. I get this gain of V over V1. In this case is going to be related to resistors, and there's an extra 2 because it turns out I got a 1K and a 1K. Gives me about 400. This is basically saying that if I make a small change in V1, I get a large change in V, which is a concept of gain. But in reverse, it turns out if I make a change in V1, it's a small change in V1. And that turns out to be very, very helpful here in terms of saying, well, what would that equivalent resistance look like? So if you've seen circuits that look like cascode circuits, this will sort of ring true to you. If not, it's just straight math. And it's the straight sort of intuition in the math we're going to build here. Once I have that, I have that'll basically, that number turns to be 400. That just put the 400 into there. And what I end up with is basically an equivalent resistance of 400 k ohms. And so it turns out you can do a lot of interesting things. Sometimes you have to do some interesting mathematical tricks to get there. There are many ways to consistently get these answers, but each way that you get there, as long as you're careful within the rules of the sort of core concepts in circuits, any of these work.